Ayan has been working closely with Rick Kessler and is part of the in-kind contribution from IUCA in India. So Ayan, please tell us all about your work.
Yes. Hi everyone. I will. So good morning, good evening, good night to people around the globe on different time zones. This is me here in India, and I'm going to give a talk today about this something very closely related to my previous speakers. Or at least along those lines. So using plastic supernova 1A cosmology with host galaxy photometric redshifts. And I've been doing this work with Rick, who is there, I suppose, for about last 1 year. And I represent IUCA India. So let's get going. Right. So this is roughly going to be the agenda of my talk. So initially we're going to get a look about the data which we used for the simulations. Basically, it's plastic supernova 1A DTF data. Then we're going to explore the cosmological analysis that we did with that. We're going to look into the systematics that we used and the how the redshift from supernova plus host and galaxy photo Z has been used. And finally, we will go to the results section where we will give a comparison of the dark energy constraints that we produced between a spectroscopic only sample and a spectroscopic plus photo Z combined sample. Right. So I start with plastic because, like I mentioned, so our supernova is based on plastic inputs. Plastic, as most of you might know, stands for a photometric LSST time series astronomical challenge. And so we use the plastic input in our simulations with DDF data, DDF standing for deep drilling field. And we used only supernova 1A without any contaminations. And where we had the spectroscopic redshifts required, we used a subset based on the foremost forecast. And the host photometric redshift were based on Melissa Graham's paper from 2018. So with all these science inputs, we still needed to get churn them all and get the light curves with which we would do the subsequent analysis. And so with that, we use the simulator called the SNIa, like Rebecca just mentioned in my previous talk. So as you might again be already familiar with, so SNIa stands for supernova analysis. It's a publicly available code, and it's broadly being used for simulations to generate realistic SN1A light curve observations for the LSST. And it also has codes to analyze these light curves additionally. For this entire pipeline of activity, we used Pippin for this, basically for this workflow. Here's one more an overview of the stages of SNIa. So we use the plastic supernova 1A plus for low redshift we had some additional complementary sample from the WFTTC2, and we produced a high stat bias score sample. For spectroscopic redshift, it was determined using the efficiency map based on foremost. And where it was not available, we would use redshift and determine from photometric redshift Z4 and Z4 error. So the simulation would essentially use host slip with this Z4 and Z4 error. So like I mentioned, in the SNIa, it has different stages of analysis, and one of the principal stage is the light curve fit stage. And so, like you heard in the previous talk, we used a 5-parameter photo Z fit with the host redshift as a Gaussian prior. It could be either spec 0 or photo Z. Subsequently, one of the following steps would be the use of the BBC, which is beams with bias correction stage. And in this stage, we would apply the bias correction and produce the redshift beamed Hubble diagram. I would like to mention that the bias corrections uses measured redshift instead of true redshift. And then we would go on to produce the stat plus systematic covariance matrix. And finally, with all those outputs, we would do a cosmology analysis, basically using the fast cosmology fitter, which is called WFIT. We used SNIa plus CMB prior. Right, so here's a couple of examples of the generated light curves. On the left, you see the low Z WFD sample shown in 6 of the LSST sparse band filters. On the right, we see the equivalent from a high Z candidate from the DTF field. And this slide shows you an example of the photometric redshift quality. So we see a couple of plots on the left, as we see as it's written, it is for the all generated events photo Z residuals. And on the right, we see the after the trigger and the selection cut stages, and the y-axis being replaced with the sol to fitted redshift. And this is used for the science case, basically, meaning the Hubble diagram. So on each panel, the sigma that you see is from a Gaussian fit from the delta Z, which is Z thought minus Z true distribution. And as you see on the label, the F out corresponds to the outlier fraction. This is what you see as the criteria for that. So we move on to the cosmology results using having understood the inputs and the light curves that we generated and a bit of their quality. So before we move forward, I would like to give a disclaimer that recently there's been a lot of interest about cosmology from using unbinned Hubble diagram. And it has been shown, for example, like Brought's paper, that unbinned results produce smaller uncertainties. And so we also tried to explore that. However, we found that the unbinned results in our case are producing a large bias, mostly caused by the calibration systematics. And so therefore we presented here in we did the analysis with only binned results. We did do a lot of backdoor investigations, and but it's still not resolved. Some of which included understanding how to have better precision for inverting a very big matrix like a 5K times 5K, or using speed tricks when we're doing the fast cosmology with WFIT, and still preserving the accuracy and time. But at the moment, so we will only present results with the binned Hubble diagram in perspective. So this is how the output sample would look like ideally. So it's a mix of spectroscopy candidates, which corresponds to the blue bars that you see on the right, at mostly populating the low redshift. And you have the photometric candidates at the high redshift, which is the sorry, I mean the spectroscopic are the red, I beg your pardon, and photometric is the blue bars on the more populated on the right of the plot. And so the resulting outputs are redshift binned Hubble diagram as a combination of those candidates as you see over here. This long red peak that you see at really low redshift, which corresponds to about 0.06, specifically marks the low redshift candidates from the WFD. And here are is a table that outlines the systematics that we considered for our analysis. Broadly, it can be broken up into calibration systematics, redshift systematics, and we also did an analysis of stat only, which is in the first row of the table. So with all of those together, we get to the Hubble diagram at the moment. So on the left, we see for the spec only, meaning only spectroscopic samples, and on the right, the equivalent of a spectroscopic plus photo Z candidates Hubble diagram. And mostly the takeaway is that we see from the residual plot on the bottom panels of either of those that there's no evident systematic trend to be seen in the distance estimates. So here's an interesting plot which is showing the uncertainty on the distance, and this is comparing between the red and the blue, which corresponds to the photometric and the spectroscopic respectively. And as we see that for Z less than 0.6, they're basically identical. But as we go towards the right of the plot, we see that the blue curve, which corresponds to the spec plus photo Z cases, give a significantly smaller uncertainty compared to the red, which is the spectroscopic only. And this can be a bit further compared if we were to just do an analysis with complete true redshift, which you call as the Z-JIT. And so here we see this, which is the green curve. And very much the blue line, which corresponds to the spec plus photo, follows it to the high Z, except for the tiny amount of improvement that we get at the really high Z when you compare between the green and the blue. So the main takeaway anyway is that using a photometric plus spectroscopic sample gives a much improved distance uncertainty much over the spec sample only. And so this brings us to the dark energy results. So here we see a pair of red and blue, red and blue of ellipses, and one solid, one dashed. So basically we're comparing between the spectroscopic and the photometric for two cases where there's a stat plus systematic only, stat plus systematic, and there's a stat only. And in either of those pairs, we see that dark energy constraints has a better figure of merit for the blue, which is the photometric case. Which you quantify on the right. So if we see, so it says photo Z cases has a better figure of merit over the spec only by as much as 40% improvement. And of course, we use this formula, which is from the Dark Energy Task Force for computing our FOM. So also we understood that using different kind of systematics would also there was a trend of decreasing in the figure of merits amount, and so we compared and we checked the ratios of with respect to the systematic figure of merit, and we see as that the calibration system, with respect to statistical only figure of merit. And we see that the calibration systematic cases eats much of your figure of merit in either cases, which is in the bottom of the table. Right. I did mention, I don't remember if I mentioned, but so we also did an weighted mean of 25 simulations, something what my previous speaker spoke about, like I think 150. So we did a weighted mean of 25 simulations to get an understanding of the bias. And so the red cross and the blue cross that you see corresponds to those weighted means of on the dark energy plane. And we see that the as expected from the previous results, that the red, which corresponds to the spectroscopy, has a bigger bias compared to the blue cross. I also mentioned about the unbinned case. So I just wanted to show the audience about, just to give a flavor, so what can be expected. So in the unbinned case, we see that the bias is way bigger for both the spec and the photo, but the spec case goes way beyond. And so we're at the moment not in a place to use those for analysis. This brings towards the last part of my talk. So the future, what we're looking ahead is that basically we're looking to do a further analysis where we would include core collapse contamination in simulation, because at the moment we only considered a pure supernova 1A sample. We would also look to use misassociated hosts in the simulation. And then because of the contamination, we would use photometric classifier and beams in the analysis, and also try to resolve the unbinned bias that I mentioned in the previous slides. And so I will finish with the conclusion. So the main takeaway message that I would like to project is that adding supernova plus host photometric photo Z significantly improves the average distance measurements for Z greater than 0.6. We also see that the figure of merit on the W0WA plane improves by about 40%, and this even including systematics, in contrast to like many previous analyses where only a statistical case would be considered. For the WCDM, however, there's a minimal improvement we saw using PhotoZ. And in the last, so all these results is part of the paper, which is currently at the moment in desk internal review. And yeah, so that brings to the end of my talk. Thank you.
Hi, really nice talk. I was wondering if you could talk a little bit more about your plan for introducing host galaxy misassociations and what impact you think that might have on your results.
What impact, I cannot give a number on that. But I would like to mention that when we would actually use the host galaxy misassociation, we would also have some other additional improvement when I'm talking about the next project in mind. So we would use a bigger data set, because at the moment we used only 3-year forecast. So I'm optimistic to say that maybe it'll not be that much. Initially, if you just use host galaxy misassociation, I would expect to be a more biased result, but maybe with other assumptions in the picture, it could be better than what we expect. But I cannot give a quantitative number on that at the moment. I don't know if that answers the question.
Alex says yes. Thanks for a great talk, Ayan. This is Gautam Narayan. I have a quick question. If you could go back to that distance uncertainty versus redshift slide that you showed with the Z cheat. Yeah, so what the heck is going on at really low redshift? How is not using the true redshift somehow
That's a
worse
statistical fluctuation, because at that bean we just happened to have very few candidates. So the cheat had that bean 1 or 2 samples. So it's just a statistical fluctuations compared to the other beans of spectroscopic or spec plus photo.
Can I ask a follow-up? And if I might ask a quick follow-up, for the issue that you were saying with the unbinned sample, does that have any, are the biases different there if you use Z cheat versus as well? So
right. So
answer.
yeah, we have been recently speculating this question, but I haven't done that comparison with Z cheat for unbinned, but I'm interested to look on that.
What's that? Oh, hi,
Sorry.
this is Dylan. I remember talking with Rick about this bias, and at the time he was telling me you were using inflated calibration systematics. Is that still the case here?
Can
this
you
is different.
Right. This one, do you mean this one? No, so can you please define when you mean inflated systematics?
I think I may have confused you because Rick was talking to me previously about DES, not desk. So
sure. Okay.
Okay.
Raul, you can go ahead and unmute and ask your question.
Thanks. So can you say once more what Z-cheat is supposed to be? Is this just using the
Z-
correct redshift?
Right. So Z-cheat is basically using true red Z true, basically true redshift. So it's the maximum amount of improvement that you can expect.
Okay, so I mean, isn't that essentially a 1/square root of n type effect everywhere?
Mm, which in which part of that you can you please elaborate a
I
bit?
guess, I mean, I'm thinking that, so firstly, one thing is, presumably there are more spectroscopic supernovae in the sample at lower redshifts
Right.
than higher redshifts. Is that what is giving rise to this Z-spec versus Z-FOT effect?
Right.
And-
You do have more spectroscopic sample like here, but if you were to ask like Gautam asked about this big on the low redshift, this big
Correct.
deep, it's basically because there's very few candidates at that part, so there's just a statistical fluctuation. I don't know if that is the question we're asking. It has
Okay, let's talk later.
yeah.
Thanks.
Yeah. Okay, thank you.
Okay, one more question. This is Dylan again. Hi. So going back to the unbinned bias plot.
Right.
In your 25 simulations, is calibration of each filter varied in the actual data?
No.
So if you are analyzing it with a covariance matrix that says that there may be calibration uncertainty and your data never has it, would you expect no bias? This is a question. I'm not stating the answer. But, when you add a systematic to your analysis,
Right.
covariance,
Right.
I think you would expect your inferred cosmology to shift.
Right.
And if you're not adding it to your data, then you won't get back the cosmology that you put in your data.
Right.
But the
So can you go back to the main question once more?
My question is, are we sure that we don't expect a bias? Given how you're doing it.
Right. So I haven't thought about it. Yeah. Yeah, let me get back to you. I mean, let me just think about, and I'll get back to you with this question, maybe answer a bit more in details if that's okay.
Yeah, we should talk because this is important.
Yeah, okay.
Any other questions, online questions? All right, well, let's thank the speaker again.